Okay, I think we can start now. That means this is our week 6, and in this week we're still in chapter 3, and I will cover section 3.2 and 3.3. I know that we still have about 2 weeks before the second midterm, but you can book your time on Examity even now, because it's better to plan everything ahead rather than booking your appointment at the last minute, like we did have a few issues last time. Okay? That means just a quick reminder that you may book your time for your exam 1, exam 2 at Examity, and even the final. Okay? You can check the calendar, you know the time, you know the windows for the exam 2 and final, and you can book your appointment. Okay? That means that will be much easier and less stressful. And just a quick reminder, please really take this as an advantage, or taking the test through Examity. Okay? But what you have to do, you have to create a good environment. Pick the best room that you can, the quiet, nice room that you like. Don't make sure that nobody's entering the room. Make sure that you leave all of your notes, electronics, books, and outside the room. Okay? That means just try to be like in the classroom, during the examination time, and then you will see how easy and less stressful everything is. And do not do any suspicious eye movements, head movements. Okay, that means just a quick reminder, because I know that this is for some of us a little bit stressful, because you looking at me now, I got used to, and I have no problem with this, but some people, they don't really like the camera, they don't really like, I don't know, being watched. Nobody likes to be watched, right? But you can still try to make the situation less stressful. Okay, let's start our session. That means this week, yes, I decided to do the day session. Maybe the next week I will do the evening, because I will try to alternate, since we have different students doing different things, being different time zone. Okay, that means section 3.2 and 3.3. We will still talk about the application of the derivatives, and this section 2, 3.2 is about the mean value theorem. Okay? That means we did learn one of the theorem in section 3.1, which was the extreme value theorem. I hope we remember what it is. The extreme value theorem was the property about the continuous function. If we have a continuous function defined on the closed interval, we will always find the highest and the lowest point. That means that's basically the extreme value theorem. We also know that the highest point or the lowest point could happen at the endpoints, like wherever we cut the domain, or actually could happen at the critical number. That means the critical numbers were kind of important thing. Okay, now it's another property, the mean value theorem. That means let's see what it is. Actually, before I start the mean value theorem, we do have something like ROLLE'S theorem. Okay? That means let's see what it is. And what I will do, I will switch off my camera, because I think my laptop and the Zoom account, it's working much better if I switch off. How can I switch off? Okay. I wish to have, because I think it's better when you see me. Yeah, you at least, but you know that I'm there. Okay, that means before the mean value theorem, the ROLLE'S theorem. Of course, the ROLLE'S theorem, the name came from the mathematician who discovered this property. That means let's see what we will have. Let f be a function that satisfies the following 3 hypotheses. Function f must be continuous function, always, okay, on the closed interval from a to b. Function f also must be differentiable function on the open interval. because we remember we do not have derivative at the endpoints. That's we're not including the endpoints. And the third condition is the endpoints, the value for the endpoints, they have to be the same. And then there is a number c in that interval that the derivative at c is 0. Okay, that's mean one thing that I didn't mention, all of these theorems, like even from chapter 1, intermediate value theorem, I hope you remember, that's mean intermediate value theorem, extreme value theorem. Now the Rolle's and the mean value theorem, which I will introduce in a minute, we call them existence theorem, because you can see in this definition, in this theorem, that having a function and satisfying all of this hypothesis, we are proving that something exists. Yes, then there is a number c in that interval that satisfies this condition. The derivative at c is 0. That means sometimes we don't even have to compute the value c. We will just prove that the c is like between a and b. Like whatever, I can take number line, let's say an interval from maybe even smaller, from 2 to 3. Okay, that means this is my interval from a to b, which is from, and then if the function is continuous, differentiable, and the value at the endpoint is the same, we will always find a point in that interval that will satisfy this condition. That means, let's say the value at a must be exactly the same like value at 3, and I can draw a function, maybe something like that. Okay, as we can see, it's continuous function, nice and smooth, no corners, no jumps. That means function is differentiable. And now, actually, what I did, I even create 2 values of c, because what we need, derivative 0 means the tangent line at this point c is horizontal. That means I see one horizontal tangent, and I can see that's my point c. F prime at c is 0, because if derivative is 0, slope of the tangent. And actually, I have another point. I may have multiple points. Okay? That's we can see. This is the condition. Let's see. Actually, I have a graph. I mean, few graphs. That's the first one is just the constant line. The straight constant function, straight line. And of course, for the tangent line to the line is the same line, and since this is horizontal, we will have infinitely many of these points. Well, what we can see, correct? Now this one, the picture B, we do have the point C over there, and drawing a horizontal tangent, we proving that derivative, having a tangent, horizontal tangent, we proving that derivative is 0. And for C, we have actually 2 points, like kind of what I did. And for D, we have another point C. And that's we can. And what I was gonna say, we don't even have to compute exactly that values. We can just prove that this value exists, and it's sometimes it's enough. Right? Another thing that we can maybe look, and I can say, let me draw something. Having an endpoint, maybe I can pick B. Value at A is here, of course, and value at B is the same. But if I will connect these 2 points, since the value is the same, they are on the same level. That means I'm also creating a horizontal line. But connecting 2 points, I am creating a secant line. Okay? Secant. That we can see the secant horizontal, and I can find at least 1 point that I can draw a tangent, which will be also horizontal, or I can say parallel. Okay? Tangent. Okay? Tangent line. That means tangent line, both of them are parallel to each other. Since this was horizontal, this is horizontal, and slope is 0. And derivative is 0. That's the kind of like a chain of properties. Okay. Let's see. I do have 2 problems for this theorem. Let's try. Verify that the following function satisfies the 3 hypotheses of Rolle's theorem on the interval from 0 to 9. And function is defined as a square root of x minus 1/3 x. That means we do have a difference between two functions, but both of them are continuous function, then the difference is also continuous function, no problem. And we also satisfying the domain. Actually, domain is all of the positive numbers, but we only taking part of this from 0 to 9. Okay, now is root x and the linear function, they are nice and smooth function. Definitely derivative exists. Okay, we can even find the derivative and prove that derivative exists for all of the numbers from 0 to 9, not including 0, not including 9. And then we have to actually check. I think I just stated that this is correct, but you can possibly help me. What's the value at 0? If I substitute 0, can you tell me what's the value at 0? I'm just trying to check if you are with me. 0, thank you, because root 0, 1/3 0. And what's the value at 9? Can you substitute 9? Square root of 9 minus 1/3 9. It's also 0. Yes, thank you. That's me. Definitely this one, I can remove it and put it again. It's correct. Okay, that means now what I know, that between 0 and 9, I can definitely find a point that drawing a tangent line at this point, tangent will be horizontal. Okay, that's the proof. And of course, from 0 to 9 is a little bit long interval, but still, I don't even have to find this point. Okay? I know that definitely the point exists because I'm satisfying all of this. That's how we sometimes prove things in mathematics. Proving all of this condition, we know that something exists. Okay, but what we will do, since the function is not really complicated, let's actually find that point. Derivative, I hope we're okay with the derivative because we need the derivative. Okay, derivative of the square root of x is 1/2 root x. Derivative of 1/3 x is just 1/3. And then I have to take this derivative. Okay? I can actually say the conclusion, f of c, or I can say f of x equals to 0. That means that x, of course, is my value c, and this will be I can write the solution of this exists as a c value, and the c value is definitely between 0 and 9. And since we have the derivative, I can solve this equation. Okay, let's try, not complicated. I think I can add 1/3 to both sides, and I can cross multiply. 2 root x is equal to 3, root x is equal to 3/2, and then I can square both sides, 9/4. Okay, and 9/4 is definitely, it's like 2 1/4 between 0 and 9. I don't know exactly how this function looks like, but I'm assuming that it's like kind of like maybe a little bit, something like that. Oh, I don't like it because it's the square root, but it's also the line. It's a combination. That means at 0 we have 0, and at 9 we have 0. And definitely somewhere inside, I think it's a little bit off, but this is my value c, because derivative at c is 0. That's c. Okay? That we can see that, as I said, we don't have to really compute. Sometimes we have to just prove it. Okay. Then I have the list of the function, and I just want to go, I would like to go really quickly through all of these 7 functions and check if, for which function below is Rolle's theorem applicable on the interval from -8 to 8. That's what we have to do. We have to check if the function is continuous, differentiable, and the value for 8 and -8 is the same. Okay, which function we can cancel out right away? What do you think? Thinking maybe about the easiest, the computation, like the value for -8 and for 8. Function 2, right? Because 8 cubed and -8 cubed is not, value at 8 is definitely not the same like value for -8. Okay, that means this is, which one? Which another one? This will be the same value, I think, because it's square, square, absolute value, square, square. And what about cube root? Cube root of 8 and cube root of negative 8? Of course, it's also different value. But even cube roots, actually, I would like to draw this function. Hopefully we know this is one of the functions that we have to know. Cube root looks like that. Yeah, it's just the inverse of x cube. And we remember function x cube has a horizontal tangent at 0. Yes, Taran, thank you. That means at 0, this function has a vertical tangent. Okay, I can say vertical tangent at 0, which means derivative vertical lines doesn't have a slope, I mean undefined. That means derivative at 0 is undefined. We can even find the formula and we will see, we will have 0 in the denominator. Okay, that means the function is continuous function, but not differentiable. And of course, the values for 8, for negative 8 is negative 2, for positive 8 is positive 2. That means the values are different. But the not having derivative is also important. That means that's not good function too. Okay, what do you think x squared? Does x squared satisfies all of this condition? Continuity, differentiable, and the value at 8, the same like value for negative 8. Do you think? Yes, of course, nice and smooth function. X squared looks like that. And can you tell me what's the value of the C number? This is negative 8, this is positive 8. What will be the C value for this one? Because function is continuous, function is differentiable, function has the same value for endpoints. That means the value C exists, that the derivative is 0. That means where is the value C? Where will be the point that I can draw? 0, of course. I can draw horizontal tangent at 0. F prime at 0 is 0. That means 0 is the C value. Okay, that works. Okay, what about this one? Number 4. Number 4 is cube root of x but squared. That means the graph looks almost the same like this one, but everything what is below we have to put above. We have to do reflection. Yes, because it's the positive values. That means the graph number 4, the graph looks actually something like that. Nice and symmetric. This and this. That means I can definitely see that value for negative 8 is the same like value for 8, because this will be cube root of 8 and squared. But what we have, where we have the problem, again, thank you, Zach, we do not have derivative at 0. Thank you, because it's just the corner. I mean sharp corner. That means derivative at 0 is unfortunately undefined. Okay, that means this function is not good. Okay, what about absolute value of x? Does this function satisfy all of the condition? Continuity, the value for 8 and negative 8, and derivatives. Okay, a little bit slim. Of course, now, what's the problem with this function? Because absolute value of negative 8 is the same like value for 8, but we have at 0, right? 0 is similar to number 4. Derivative at these corners doesn't exist. It's undefined. Okay, that means that's not good. Okay, and then I have 2 functions that they don't look friendly, but let's see. Hopefully we remember that number 6 is half of the circle. That means I will not draw it again. I will not explain again. I think I did once. But if we will solve this equation for y, we will get x squared plus y squared is 64. But since is the square root positive, we only taking the positive part from -8 to 8. Okay, that means that's number 6. And what do you think? Is this function continuous and differentiable between -8 and 8? And yes, yeah, we have nice and smooth function. We're not looking at the derivatives at the endpoints because it's open interval. That's yeah, this function is definitely good for the ROLLE'S theorem. I can indicate the zeros. And the same, the value c will be 0. Okay, that's my c point. Derivative at c, derivative at 0, of course is 0. Okay, and I have one more. X squared minus 64, absolute value. That means I'm assuming that everybody knows how to draw x squared minus 64. Okay, do you know how to, we know x squared, right? And can you just tell me what -64 does for x squared function? Please ignore the absolute value for now. That means x squared minus a number. How can I shift the function? Oh, no. X minus 8 squared is a little bit different than this one. Because if you will expand x minus 8 squared, is, I mean, we don't have to even expand. You subtracting 8 from x, that means you will shift along the x-axis. Like 8 units to the right. But this one, since we're subtracting from the entire value, we have to drop the function 64 units down. Okay, that means I can possibly draw here. That means this will be parabola x squared, but 64 units down. Okay? But now, that means this is just the function inside. How can we apply the absolute value? Absolute value of any number is positive, right? That means if we have positive numbers, like this is positive part. Positive number, absolute value of positive number is positive number. That means this part will stay. Right? This is number 7 actually. But having negative values, absolute value of negative values actually are positive. That means I have to remove this and make the reflection above the x-axis. I mean, with respect to the x-axis. That means I don't have this part. Okay? Just everything what was negative must be positive. And this, of course, is -8 and 8. And the values are the same. Okay, that means looks kind of like we're not looking at that part because we're only taking function from -8 to 8. And looks kind of like the part that we're looking for looks kind of like a half of the circle. That means this function also satisfies the condition. Continuous and differentiable, and the value c will be 0 again. Okay, I don't want to squeeze it. Okay. That means just make sure that we know how to draw the absolute value function. Okay, that means nice, check. Okay, that's me. Now let's look at the mean value theorem. I will skip, okay, I will just skip a few things, but we don't have to worry for this. Okay, that means the mean value theorem is a little bit, I mean, similar, but with the small difference. Again, you can notice that there is a number. It's also an existence theorem. That means now what we need? We need a function, okay, with two hypotheses. Function must be continuous function on the closed interval from A to B and differentiable. That means the same situation. We can't have any corners, gaps, discontinuity. I mean, continuity is in the first one, but no vertical tangents, no corners, no kinks, yeah, like corners, corners. Okay? That means nice and continuous, nice and differentiable. And now we don't have to have the same value for A and for B, the endpoints. No, function can start and can end at different level. But now, then there is a number C in that interval, then the condition of the value C is like that. Okay? That means now derivative at C, f prime at C is not 0, is equal to this, f of b minus f of a, b minus a. That means you probably realize that the right-hand side is simply a slope of the secant line. Slope of secant from A to B. Like if I will ask you, please find the slope of the secant line between A and B, you will just go with this formula. And derivative, of course, is slope of the tangent. Slope of tangent at C. Okay? That's when we can see, and we can maybe ignore this one, is just different form. That we can see is almost the same like the Rolle's theorem, except that my right-hand side is not 0. But my right-hand side, you remember I did connect these points A and B. My right-hand side also was a slope of the secant line. But since it was horizontal, was 0. Yeah, that means the same thing. And let's see. This is an example. It's a function, continuous and smooth. Blue line is connecting endpoints. And because they are not at the same level, if I will shift this and if I will put everything at the same level, then the blue line will be horizontal. Yeah, the blue line will be horizontal. And I will have graph. I'm trying to mimic the Rolle's here. Yeah, you can see it's the same, it's almost the same situation, but we not required the same value at the endpoints. That's the reason that it's like shifted. Okay, but the same idea. Slope of the secant line, connecting A and B, is exactly the same like slope of the tangent at certain point, but this point always will fall between A and B. Or if the function is more fancy, we even have 2 points. As we can see, C sub 1, C sub 2. Because blue line is connecting is the f of b minus f of a, b minus a. Right? That's the slope of the secant. And I can draw 2 tangents with the same slope. And I think I write this. The slope of the tangent line is the same like the slope of the secant. Yeah, it's really nice interpretation. That means always the value C exists in the interval A and B if the function is continuous and differentiable. Oh, we can say parallel. That's the same. Tangent line parallel to the secant line, which means they share the same slope. Okay. Okay, I have a few notes. That means if we will think about the position function, and one of the application, of course, is the velocity, the rate of change of distance over the time, we can have the mean value theorem defined like that the instantaneous velocity is exactly the same like the average velocity. Yeah. Rate of change, tangent line, secant line, or instantaneous rate of change, average rate of change. And now let's, like, I just typed this short scenario. For instance, if a car travels 180 kilometers in 2 hours, which means the average, we can quickly compute, just based on that, we can quickly compute this, because the average rate of change will be just distance over the time. 180 over 2. Let me actually write 90 kilometers per hour. Okay? That means this is that part. But what this means, when you're driving, your speedometer must have read at least once exactly 90. Okay? Which means your instantaneous rate of change. Not only the average. The average is the average, but average means that you could drive a little bit slower, a little bit faster, which I still think is quite high number, speed. Average is not really telling me that I really drove 90 kilometers per hour constantly, no. But at least once, I definitely was driving 90. Yeah, that means this will be like the instantaneous at that instant. Yeah, that means some interpretation. Let's point something else. Okay, that means that's also the good thing is we can see the main significance of the mean value theorem is that it allows us to get the information about the function from the information about the derivative. That we can see this equation is kind of like, this is derivative, and then I am saying that is exactly the same, like some, we know what this means, but it's some values just about the function. That means if you have some information about the function, f value maybe at b, value at a, b and a, then you can figure out the derivative, not even having the entire formula. And I mean, that's another thing, like you can gain some information. Okay, and I do have a few questions. Oh, okay, let's do the first one. We have the graph, that we have to use this graph to estimate the value of C. We know what C means. C is the point that satisfies the conclusion of the mean value theorem, just from the interval from 0 to 8. Let me label properly 2, 3, 4, 5, 6, 7, and 8. That means what I can use. Let's save blue for the C. That means this is 0, and that's the value for 8. I can also label 1, 2, 3, 4. That means now you can tell me, I will ask you, I will connect these green dots. Okay. That we can see these green dots, that's the secant line. And the secant line, the slope, of course, I don't have to write the equation at the moment, but because I don't even have. We can even compute. Do you think, can you tell me the slope of this? What's the slope of the green line? It's 3 over 8, rise over run, of course, because that's 3 and that's 8. Okay, that means now we're looking for the value C. Okay? Function definitely satisfies the condition that I can draw a tangent line at that C, and the tangent will be parallel to that green line. That means, do you think somewhere here, right? You can even, yes, you can even touch your screen and kind of like think at 3. Oh yeah, I think at 3. I will try to draw. Oh, yes, okay, good. And I think this is tangent. Tangent, and I can say derivative at 3 is equals to this one. Yes, the slope is the same. And okay, 2.9, yes, I think it's maybe a little bit, yes, maybe a little bit. Okay, and do you think you can give me another number that I can, 6.2, wow, you saw, yes, not, because 6 is not good. 6 will give me horizontal, but a little bit, okay, I will try to match, yeah, okay, wow, I'm actually, that's good, tangent. And the value of the derivative at 6.2, I will write this 6.2, and that was 3. It's the same, it's equal to 3.8, 3 over 8. Okay, that's, we can see, that's the idea. Yes, you did figure out the value C, which is 3 and 6.2. Yeah, as you can see, it's quite, of course, we don't really maybe appreciate at the moment, but it's quite powerful tool. Okay, let's keep moving. What we have? I will skip this one, or maybe not. I can just show, yeah, we can do this. Like we did for the ROLLE'S theorem. Verify that the following function satisfies the free hypothesis, should be actually 2, of the mean value theorem from 0 to 2. As we can see, from 0 to 2. That means, let's see. Polynomial functions, because this is polynomial, are definitely continuous functions. And definitely differentiable, because they don't have really sharp corners. And what we can do, then we know that based on the mean value theorem, there is a number C, okay? There is a number C that will satisfy the C in the interval from 0 to 2 that will satisfy this condition. derivative at C is exactly the same like the slope of the secant line, tangent line, secant line. And what we can do, since we have extremely easy function, let's find that value C. Okay? What we can do, we need the derivative. First of all, we need this. Yes, hopefully we understand. That means the value at 2, I just took 2 and substitute here. 2 cubed minus 2. 2 cubed minus 2, of course, is 6. And value at 0, of course, is 0. That means I have 6 minus 0, 2 minus 0. And everybody is okay with my left-hand side? Yeah, it's just simply the derivative. It's the derivative of the function. 3x squared minus 1. But I did put c instead of x. Okay, and then I have just the equation, quadratic equation, but then I can solve for c. This is 6 over 2 is 3, 3 plus 1 is 4, divide by, oh, too fast. Maybe I can write one more step. C squared is 4 over 3, and then I took the square root of both sides. That means I have a number positive 2 over root 3 and negative 2 over root 3. Since I'm only talking about my interval from 0 to 2, I can only accept positive number. Of course, this number the negative will also give me the tangent parallel to the secant, but this is outside of my interval. Okay. That means this number is definitely, I believe 2 divided by square root of 3 is less than 2. Must be less than 2. That means this is definitely a number, even without the calculator. We know that this is even less than 1, but it's greater than 0. That means it's definitely in that interval. And that means this, I can maybe change color. That's the mean value theorem. That means please remember that property. Secant tangent, easy. Okay, let's see my other questions. Oh, we do have this function. And that we can see, this is, the blue actually is secant. And C is simply 2 over square root of 3. We do have another, I mean, it's on the other side, okay, it's not on the graph, I'm not gonna label. Okay, but we can see the tangent is parallel to the secant. Okay, and yes, let's do this one. That's the typical, I would say, quiz question. Okay, you can try, I mean, you can try to solve it, or we can solve it together, of course. If you're watching later, maybe you can pause the video and try to solve it, and then you can compare to my solution. Okay, find the number C that satisfies the conclusion of the mean value theorem for the function 9x squared plus 5x plus 6 between negative 5 and 5. Okay, nothing almost to check because function is continuous and differentiable. But now, oh, I didn't type. I thought that I typed at least a property. Okay, we're looking for C from the mean value theorem. Derivative at C is exactly the same like f of b, f of a, b minus a. Derivative at C, and my b and a is negative 5 and 5. That's f of negative 5 minus f of 5, negative 5 minus 5. Am I right? Actually, I can keep it like that, but actually, let me change for the second number, 5. You can switch the numbers. It will be the same thing, but you have to line them up. If this is f of 5, this must be 5. If this is f of negative 5, this must be negative 5. I will just avoid. The first form was also correct, because you can also switch, which actually, I can write it for you. F of A minus F of B, but then A minus B. Line up A's and B's. Okay, that's we have to solve this equation. All of the value on the right-hand side will be the constant, and this will be the derivative. That means, who can tell me what's the derivative of the function? Who can tell me the derivative of 9x squared plus 5x plus 6? And I can copy from the chat box 18x plus 5. Excellent. That's mean 18, but I will put C. 18x plus 5, 18c plus 5. Okay, and then I need your help with the arithmetic. 5 plus 5 is 10. I can do this, but now we need the value at 5. 9 times 5 squared plus 5 times 5 plus 6. 9 times 25 plus another 25 plus 6. So this is 9 times 25, and this is additional 25. That's mean altogether is 10 times 25. All right, that means that's easy. 10 times 25 is 250, and plus 6, 256. Wow, that's easy. And let's try to get the value at negative 5. 9 times negative 5 squared will be 25. 5 times negative 5 is minus 25. Okay, that's me now. I have 9 times 25, and I'm subtracting 125. That means this will be 8 times. 8 times 25. That means 8 times 25 is just 2 25s less than 250, which is 200. And plus 6, 206. Okay, and now we will solve this equation for C. Hopefully the C value is between negative 5 and 5. You see that means even like without solving at the moment, somebody will tell me, you can predict. Yes, you can definitely say, still the interval is a little bit too wide, but you can tell me that the value will be definitely between negative 5 and 5. Okay, let's check. Okay, who can tell me the number on the right-hand side? 250, it's 5, I think. 50 over 10. Oh, okay, 5 and 5. That means 18c is 0. Oh, okay. Not really funny number, I mean important number. Okay, that means this is my value C, and it's definitely in that interval. It's actually exactly in the middle. That's not the case, it's just the coincidence. No, don't pick 0. We really have a reason to have 0. Okay, that's me, please. I can box it for you. You will need this. Okay, let's do what I have. That means this kind of question, yes, make sure that you know how to deal with this equation. Okay. Okay, let's look at the next one. Suppose that f of 0 is negative 3 and f prime of x is less than or equal to 5 for all values. Oh, interesting. For all values of x. How large can f of 2 possibly be? Of course, when we're reading this for the like first time, and if this will be like the question somewhere, like I will not even know maybe what to, I mean, probably I will try a few things, but it's not easy to identify that we can use the mean value theorem. Okay? But do you remember one of my notes? Mean value theorem is the property that is connected, like we can get some information about the values of having the information about the values of the function, we can kind of like recover the information about the derivative, or the other way. Having some information about the derivative, I can figure out what is the possible value of f of 2, the largest possible value. Okay. That's, of course, we can do, did I type this question? Okay, I did type this question. I don't want to show you, I mean, I will show you, but I also want you to think and get the answer like kind of drawing the stuff. Oh, okay, that means I did type this function. Since the function has derivative, yes, we can see derivative is defined. It's less than or equal to 5 for all of the values. Then I'm assuming that function is continuous and differentiable. That's the reason that I can use the mean value theorem on the interval from 0 to 2, because the information for 0 is given, the information for 2 is required. So what I will do, let's try
We can, of course, we can put the equation in, but let's try to plot this. F of 0 is negative 3. That means this is 0. 1, 2. Value at 2, actually, we don't know the value at 2. That it could be one of my dots. Yeah, I don't know. Could be, maybe the value is 1, maybe 2, maybe negative 1, maybe negative 10. I don't know. They have to find me the largest possible. Who can tell me what this means? F prime is less than or equal to 5. Graphically, what derivative means graphically? Do you remember? You remember. I always refer this. It's the it's the slope. Yes. That means x can only rise as 5. That means 5 actually is the maximum. Is the maximum slope of the tangent line, because derivative means the slope of the tangent line. That means I will kind of, when you picture the mean value theorem equation, this is my left hand side. That means I don't know, I'm just guessing, let's say 5. Okay? That means slope is 5. That means if this slope, of course, this is the maximum, because all of the other tangents, they have to have slope less. Yes, we can say this is maximum, which means that blue dot must give me the maximum value of 2. And can you see what this blue dot is? I can use maybe different color. Oh, that's too better. Okay, we know this distance. This distance is 2. Run. I don't want to mess up. That means, what do you think? What rise must be in order to have the slope 5? Because it's rise over run. That means that this, what will be this distance between the blue dot and the green dot, let's say? Okay, we don't know. Let's say A. That means A over 2, which is rise. Actually, I can say just rise. I don't have to introduce another. Rise over run must be 5. Right? Oh, yes, I see the correct answer. That means rise over 2 is 5, which means rise must be 10. Make sense? That means between the green dot and the blue dot, we have to have 10 units. And how many units we have below the x-axis? I see your answer, Karen, I see. But let's just see, that means you see the whole green line must be 10. And we do have 3 units below the x-axis. That means we need 7. I can actually use the blue color. 3 plus 7, of course, is 10. That means the maximum value of 2 is 7. Now we can see how easy we can figure out, and it's nothing complicated, and I would even say nothing new. Of course, we have to know that this red box represents the slope. We know that. Okay, but what we can do, I do have nice formal solution. Mean value theorem, f prime at c is the same like f of 2 minus f of 0, 2 minus 0. Okay, and the maximum value of the derivative is 5. Because we're looking for the maximum value of 2. And then the value at negative 3 was 0. I multiply 2 times 5 is 10. No, hang on. We don't need f of 0. F of 0 is negative 3. F of 0 is negative. That means negative and negative will give me positive. Multiplying, cross multiplying, I got 10. And subtracting 3, we're getting the same answer. Okay, that we can see based on the equation or just based on the kind of like a common sense. Hey, this is also a nice question. Okay, I do have another one like that, but I will leave it, this one for you. Yeah, now it's how small f of 7 could be. Or would you like to go through this question? Or you prefer to do on your own later?
We can leave it, okay? No preference. Oh, no, I don't want you to see this. That's the same question. That's the same question. And this. That's me. What I will do, I kind of jump. I did type the solution for you. That's me. Please maybe pause the video. Don't look at the solution and try to get these numbers. Right? Good practice. Okay, that's what we have. We do have one more part. Maybe like I need another half an hour. Yeah, I hope you can stay with me. Hopefully it's not a night. That's we can still carry on. Okay, that's mean that the other section for this week is 3.3. How derivatives affects the shape of the graph. Okay? Which again, if you really understand the derivative, probably all of the things that I'm gonna say are the common sense. Let's see. First of all, what does the first derivative is saying about the function? That means let's look at the blue curve. Right? We can see the blue curve, and I draw a tangent lines. And what we can say from A to B, function is increasing or decreasing? Who can tell me this? From A to B and from C to D. Oh, it's increasing. Yes, thank you. That means function is increasing. Oh, okay. Oh, too much. I thought, okay. Function is increasing and increasing. From B to C, of course, is decreasing. And now, can you tell me the slope of the tangent line? The slope of the tangent line is positive or is negative when the function is increasing? Like all of these slopes at the increasing part. That slope, that one. Slope of the tangent, it's positive. Okay, and what about the decreasing part? What about the slope of the tangent? Can you tell me about it's negative? Thank you. That means this is the important information. Let me show you this. If function is increasing, the derivative is positive because that's the slope of the tangent. If function is decreasing, derivative is negative. Okay, that means that's quite easy. Okay, but we have to, for this one, we have to make sure that we understand what increasing and what positive means, and respectively decreasing and negative. Okay, because we shouldn't be confused with the increasing and positive, negative and decreasing. Okay? But for now, it's okay. If the function is increasing, derivative is positive, decreasing, negative. Okay, that means this is the increasing, decreasing test. If I will ask for the intervals of increase or decrease, you can set up this inequality for the increasing, or derivative is less than 0 for decreasing. And that's it. But what is important also, let me come back to this one. Let's look at the point B and point C. What do you think? Do we have a special name for the point B and point C? I can maybe make thicker. How do we call the point B? And how do we call point C? Do you remember from last week? Oh, come on, we still have, I hope you're not sleeping. I know that you're not. It's oh no, okay, I still didn't, okay, more general. This is correct because this is locally highest point, locally lowest point, but how can we name them more generally? Like what was the name? Do you remember the quiz from last week? What was the main question? Find. Of course, I asked you for the extreme value theorem, but I asked you to, critical points. Thank you. I'm looking for this. That's actually the B and C. That's the critical points. That we can see how important they are, because in order to find the intervals of increase or intervals of decrease, I always have to start with my critical points, because critical points are kind of like the boundary, like this will be like the derivative will change the sign. We can see function is increasing and then is attaining critical point. Of course, we know that is maximum at this point, and then is decreasing, and again, changing for the increasing, we also meeting a critical point. That means all of the changes are happening at critical points. Okay, that means now, having a function, just the 4th degree polynomial, we have to find the intervals of increase and decrease. That means just what I said, the first exercise will be to find a critical points and then solve the inequality. Since this is polynomial, domain are all of the real numbers. That means I shouldn't be worried, because we also remember critical points are the points in the domain. If some numbers are not in the domain, we're not including them. Okay, that means this is function 3x to the power of 4 minus 4x cubed minus 12x squared plus 5. Now derivative, I hope you agree. You can always check if I didn't make any typo, because I think I can get that derivative. 12x cubed, 12x squared, 24x. Okay, and now I will solve.
First of all, this equation. Remember, this is giving me critical points. And this is for critical numbers.
Okay, that means I took the derivative. I can see the common factor 12x. I factor out 12x, and I have quadratic expression. And this quadratic expression I can still factor out, because the product form, the factored form, are the easiest form to get the zeros. And now I can see 0, negative 1, and 2. 0, negative 1, and 2. That's my critical points. And what I will do, since I have to solve this inequality and this one, okay, which means this will be something like that, greater than 0 or less than 0. That when we remember, we need a number line. We have to put all of the zeros on the number line. And this is like a college algebra question. And now I have to test each interval for positive or negative numbers. Yeah? We can pick any value, doesn't really matter. We can pick any value from that interval, and this will give me the sign. And then I have to test my derivative, because this is my derivative, and I want this derivative, the blue box is the derivative, and I want this derivative to be positive for the increase, to be negative or decrease. That's what I did. I took all of the factors, 12x, x plus 1, x minus 2, and I will be testing the sign. Did I did this? No? Okay, I can do it. That means what I will do, I will pick a test value negative 2, maybe. And if I will put 12 times negative 2 is negative 2 plus 1 is negative 2 and negative 2 is negative. Negative times negative times negative will give me negative value. That means from negative infinity to negative 1, we have decreasing factor. Because this one, I'm testing the sign of the derivative. Since I'm using red color, I will. Okay, let's take a number from here. Oh, that's small interval. Okay, let's take negative half. 12 times negative half, negative. Negative half plus 1, positive. Negative half and negative 2, negative. Negative times positive times negative will give me positive. Okay, let's take the test value 1. 12 times 1, positive. 1 plus 1, positive. 1 minus 2, negative. Positive times negative, negative. And let's take 3. 12 times 3, 3 plus 1, 3 minus 2. Both of them are, all of them are positive. Positive times positive times positive, it's positive. Okay, that we can see. The intervals of increase, I can maybe use increase will be this one, wherever is positive. That interval is positive, and this interval is positive. Okay, and the intervals of decrease, negative. This one is negative, and this one is negative. Okay, that means that's the way to solve inequality. Of course, you remember, I decided to go and show you. Also, important comment. I don't know what is the time of the session, but please remember, these signs, they do not alternate always. Okay, because you can think, oh, I can find one and then I can alternate. No, sometimes we may have two negatives, two positives next to each other. Okay, you know, increase and decrease. Okay, oh, I have the table a little bit different way, but that's how this works. What we had -1, I can use red color, -1, oh, am I? 2 and 0, the critical numbers, -1, 0, and 2. Yes, we're looking for the critical points, horizontal tangent, I can draw it. And we can see decreasing was from -infinity to -1, and from 0 to 2, and increasing was from -1 to 0, and from 2 to infinity. Yes, we can see we do have, oh, I should use the blue color, but it's okay. Okay, let's keep working. That's me now. What we have now is the moment, because I think I've got few questions, even on the discussion board. Somebody asked me, how can we identify local maximum or local minimum having a critical numbers? Okay, that's we do have a special test, and we call first derivative test. And looks like that. Oh, okay, we can see. Now, first of all, we have to compute a critical numbers. Okay? Now, having a critical numbers, we have to check how derivatives behaves from the left and the right hand side at that number. And we can see if function is increasing on the left and decreasing, of course, the function attains local maximum at C. Of course, the common sense. If derivative is positive and then negative, local maximum. If the situation is the other way, local minimum. That's mean we really have to check, we have to find the critical numbers, but also we have to check sign of the derivative. Derivative negative, derivative positive, local minimum. Derivative positive, derivative negative, local maximum. Okay, actually, let's come back to this. That's mean, what do you think? Of course, I can show you the graph, it's easier, but what do you think? What is happening at -1? Does function attain maximum or minimum? We can see negative. I can, what color I can use? It's the minimum, right? Because function is decreasing and then is increasing. This will be, let me put local minimum. And then what is happening at 0? Function is increasing and then is decreasing. What is happening at 0? And you can nicely see the wave. Local maximum. And then function is decreasing and then again increasing. At 2, we have local minimum. We can nicely see a happy valley and a summit, Tassie Mountain. Okay, happy valley. And that's mean minimum, minimum, maximum. Always this, the negative represents decreasing. Positive derivative represents function being increasing, and so on. And we can see, yeah, this is the graph. That's maximum. That's the graph. That means that's easier. We still didn't really get this. Okay. Oh, not maximum, of course, minimum. Okay, minimum, maximum, minimum. Okay, that means that's, even if this slide looks so obvious, but this is the first derivative test. Okay? We have maximum, we have minimum. We can also, we have to be careful, because having a critical point, okay, not always function will attain maximum or minimum. because we know what to do. We have to check the derivative. If the derivative is positive, function is increasing, we can see we do have this moment with horizontal tangent, critical point, and again is increasing. That means increasing and increasing, positive, positive. No extreme value, no local extreme value, or the other way. But please remember, not always, not all of the critical points will give me local extreme values. That's the same. No, that's actually the same question, but we identify. I can maybe draw it again. How was it? Derivative was negative, positive, negative, positive. Then function is decreasing, increasing, decreasing, increasing. Local minimum, local maximum, because that's what you will do a lot for the next 2 weeks. Okay. I will skip this one. And this will be the last thing, because we also have shape of the function like that. As you can see, function is, both of the functions are increasing, of course. From A to B is increasing, and from A to B on the other part is also increasing. But you can probably see the difference. Can you see the difference? Can you see? Yes, the functions definitely looks a little bit different. And at the moment, I can say that they are bended in different directions. They are kind of bended like this way, and this one is bended this way. We do have a special word for that. Okay, but let's identify something, because now the question is, what does the second derivative say about a function? That means this is the same graphs with the tangent lines. That we can see slope of the tangent is positive, slope of the tangent is positive for both of them, because function is increasing. Of course, nothing special. We just went through this. But now let's look closely how the slopes on itself behaves. That means, what are the values of the slope? Let's see, this is quite small number, right? Is this slope greater than this one, the first one? What do you think? If the line is steeper, is the slope greater? Can you see how the lines are getting steeper and steeper? Yes, thank you for answering my question. I really appreciate that. That we can see slope. Okay? Slope is increasing. Okay, and what about the second one? Slope is quite steep, a little bit less, and almost horizontal. That means slope of the tangent is decreasing. And how can we define slope with respect to the function? Can we say that slope is the derivative? Because of course this is slope of the tangent. Okay? That means, what we just learned, if something is increasing, what's happened with its derivative? If something is increasing, derivative is positive. That means, now let's see, because I don't want to use the word function. That means, if the slope, yes, if this blue circle is increasing, because we can see it's increasing, its derivative is positive. That means, can you see what I created? I created the second derivative, because my blue circle, whatever it is, slope, if the blue circle is increasing, its derivative must be positive. Which means, if the function is bended this way, always the second derivative will be positive. And let's see on this side. If my blue circle is decreasing, its derivative, that's derivative, is less than 0. Which means the second derivative must be negative for the function to be bended this way. Yeah, nice and easy proof. Let's see, I typed this everything for you. That means, that's what I said. F prime is increasing, its derivative is positive, which I can say
second derivative is positive. If the slope is decreasing, slope, I have to circle everything, second derivative, its derivative is negative. Oh, okay, that means this is the proof for the function to be bended up and down. And do you know a special word for the function to be bended up and down? Because I have on my next slide. No, okay, I can show you. Yes, concavity. Thank you, Erica. That's actually, we can say that function is actually concave upwards or concave downwards. That means this is up, okay? This is down, when it's like open down. Okay? Of course, I'm overexcited. Okay, that's me. But what we call concave up and concave down. And we do have concavity test. We simply have to check, that's what I did. That's what I'll show you. We have to check the second derivative. The second derivative must be positive or negative. Of course, it's similar situation to the first derivative. In order to solve these inequalities, we first of all have to solve the second derivative for zeros. The solution of this equation, we don't really call like critical numbers, but they are still important numbers. And I can show you, okay, that we can see the graph and function is changing concavity at B, at C, at D, concave up and down. Oh, it's not really changing at E, but something is going on. And we're changing at P. That we can see function is concave down, and then from B to C is up. From C to D is down, and then it's up. And again is up, okay, and then down. That means what we will call the numbers that the function is changing concavity, we call inflection points. Right? That means in order to find the inflection point, we have to solve this equation. Second derivative is 0. But please remember, not all of the numbers from this equation will give me inflection point, because inflection point means that function is changing. It's changing from concave up to concave down. Can you notice the point E? Yes, function is not, probably point E will be the solution of this equation. But what we have to do, we have to check the sign. Second derivative positive, second derivative positive. Like on both sides. That means point E is not really an inflection point, but it's still the solution, for this equation. That means in order to get a potential inflection point, we have to solve this equation and still test the sign of the derivative. Okay. Okay, and I do have function, quite, yes, and let's just, this will be our last exercise. That's what we can do. We can quickly find the intervals of increase and decrease, local maximum, minimum, and then intervals of concavity and inflection points. That's me, nice and easy function, domain, all of the real numbers, okay? And then we need the first derivative, 6x squared minus 6x minus 12, solve the derivative for 0 to get critical points. And we can see my critical points are 2 and -1. Okay? Or second derivative. But what we can do, okay, let's find the second derivative. Second derivative is just 12x minus 6. Second derivative is 0 if x is half. And did I do? Okay, I didn't really do it. That's mean what I will do. I will draw a number line with critical points. That means this is my first derivative. Right? And I'm testing my first derivative. Again, because I have to check if this will give me local maximum or local minimum. You can probably, I can draw a little bit higher. Okay, let's put
I mean, we can do the test. Let's do the test value, -2. If I put -2 times -2 and -2 is -4. That means it's negative number. And -2 plus 1 is also negative. That means negative times negative will give me positive. I can pick 0. 0 minus -2 is -2. 0 plus 1 is 1. -2 times 1 is actually negative. And I can pick 3 or even 300, positive, positive. Okay, that means function is increasing, decreasing, increasing. Can you tell me what is happening at -1? Local maximum or local minimum? Or at -1, it's maximum, of course, because it's on the top. And at 2, what is happening at 2? Local minimum. Thank you, Zach. Okay, now let's take a number line for the second derivative. 1/2. That means if I will take, this is just the second derivative. If I will take 0, I have negative. If I will take 1, I have positive. And now this means that function is concave down and concave up. That means it's definitely changing a concavity. At 1/2, we have inflection point. Okay, and now how can we draw this function? I mean, you can probably put all of the information together, but I kind of did, I put all of them in one table. That we can see, this is first derivative line, this is the second derivative, and that's function. 0 was, I mean 1/2 was the 0 of the second derivative. -1 and 2 was the 0 of the first derivative. Okay? And this is an interval from -infinity to -1, from -1 to 1/2. This is like entire number line, from 1/2 to 2, and from 2 to positive infinity. And let's check positive, negative, positive. That means positive, negative, positive. And the second derivative was negative and positive. Negative on left, positive on the right. Okay, that means I can nicely see that function is increasing concave down. That means something like that, increasing concave down, local maximum. And then it's increasing concave, and it's actually the inflection point. Oh, how can I draw it? Okay, let me just draw it like that. And then it's inflection point, and now function is still increasing, but concave up. And then it's local minimum and up local maximum. That we can nicely see the shape of the function. That's what I was gonna almost a little bit. Inflection point. Simply, okay. Inflection point, local maximum, and local minimum. Of course, you can use more space. We don't have -1. I don't know exactly the values, but looks like that. -1, 1/2, and 2. Probably I can still shift the function up on the, or down, because I don't know exactly the values, but something like that. We can see we definitely respect the first and the second derivative. Okay, I will finish. I still have few questions in this section, but I think I typed the answers. That means you can check the answers, but that's all of the concept for this week. That means please even like watch this session every day, for just maybe for like, you can divide it for a few minutes and make sure that you understand all of the concepts covered. Thank you.